Good morning, folks. I hope you enjoyed your Friday off of lectures. Um, just a few small announcements before we get started today. First thing you should know is this is the last week that I'm going to be lecturing to you guys in this format. Starting next week, we're going to take a look at your student-led lectures, your presentation assignments, which I'll remind everyone are due this Friday as YouTube videos. And so what I'll do is I'll continue to put a lecture discussion page together for our 3 days class next week. And I'll probably add a little bit of narrative to those discussions just in terms of text, right? I'll probably just um, lay a little bit of text down in the discussion and then put, your student video in there. We'll probably be looking at 2 to 3 student presentations a day just to get through we have 8 groups, I think, all 8 of them next week. Yeah, and that's what that'll look like. So we are in the home stretch here. Second announcement is that I am still working on grading exam 2. And the thing that's slowing me down there is that this digital format is making it a lot harder to give you guys quality feedback. I can't just do my usual thing of writing notes on the screen or on the paper rather. And so that's a little bit tricky. So still working on that. Whenever that's done, I'll probably post, I'll definitely post a key, and I'll probably post a little video walkthrough, at least if we see some problems that people are consistently having trouble with. And so that will be posted not as a lecture, but as an extra piece of information whenever we've got that. But so for today, we've been talking about electrophoresis as a separation technique, and we've seen kind of the fundamentals. That's electroosmosis and electrophoresis as the two mechanisms that make these separations happen. Today, I want to take a closer look at the specific instrumentation for CE. Instrumentation, I think I spelled that right, for CE. Okay, and we're going to start with the first part of the instrumentation, something we've already talked a little bit about. Some people still call this the column. That's not as common. That's usually when you have a separation scientist trying to someone who does HPLC trying to talk about CE, they'll often call this the column. The rest of us, the people who are trained from the start in CE, call this the capillary. This is where all the magic happens. This is the physical space where all of those electroosmosis and electrophoresis mechanisms happen. Let's take a look at this capillary. So it's a cylindrical tube like this. It has an inner diameter and an outer diameter. Let's label those. We'll call the inner diameter ID and the outer diameter OD. Outer diameter, inner diameter. This capillary has a total length from the inlet to the outlet. We're going to call that L subtotal. Somewhere along this capillary, though, we're going to place an on-column detector. We'll talk more about detectors in the second video today. But here's a detector. And of course, if this is where we detect our sample, well, all of the electrophoresis and electroosmosis that happens down here, we never observe that, right? So we actually have a second length that we think about, and that's the length from the inlet to the detector. And we generally call that the effective length. I'm going to go L sub EF, F for effective. So that's the effective length. That's the total length. Let's see here, L total. This is typically on the order of 30 plus centimeters. So you see these things very long sometimes, but 30 centimeters is kind of a typical value. It's usually the smallest value you can fit into a commercial CE instrument, usually, unless you modify the instrument. And the reason we care about L total, even though we're observing only a separation across L effective, is that the total length is what's used when we consider the electric field, right? So the total length dictates the electric field strength. So if I apply 30 kilovolts across a 30 centimeter total capillary length, I am getting a field, even in the L effective region, I'm getting a field of 1,000 volts per centimeter, right? 30 kilovolts, 30,000 volts over 30 centimeters. Okay, L effective is usually, so it's typically about 5 to 10 centimeters shorter than L total. And we've seen what this means. This is the actual distance over which the separation happens. So it is very common to see lengths in the literature reported as the effective capillary length. This is what they're talking about. Okay, inner diameters. These are typically less than 100 microns. And we need those small dimensions. We saw this before. We need these small dimensions to dissipate, let's say dissipate heat. Dissipate heat, there we go. So we need these small dimensions to dissipate heat, and that's why we rarely ever see CE being done with anything larger than 100 microns. What's more typical is 25, 50, 75 microns. 100 microns would be a pretty big capillary um, for doing CE. The outer diameter, this is very common, 360 microns, and all that is a standard size. It doesn't actually, for the most part, play any role in the separation, but it's used for common fluidic connections. So if you want to connect a syringe or some kind of pump to this capillary, any other kind of tubing that you need to connect to this thing, they make standard commercial connections that are designed to work with tubing in that outer diameter, and so that's what's most common. You actually can get this in different outer diameters. They're available anywhere from like 150 micron outer diameter, which can be pretty common in some CEMS instrumentation, all the way up to like 500 micron outer diameter. I haven't seen a good application for larger diameters than 360. Okay, so the material is fused silica. We talked a little bit about this material. It's the same stuff that GC columns are made of, right? So it's this glass. It's basically a pure glass. Fused silica is just pure silicon dioxide. There's no dopants in it. And just like in the GC capillaries, it's wrapped in that polyimide coating so that it can be bent a little bit to work in our favor in orienting the instrument. We choose this material because it's generally chemically inert, so we're not too worried about. So adsorption we worry about, but we're not worried about actual chemical interaction, like reactions happening at the surface. It's transparent, and that's good. That's good because we're going to do this on-column detection thing. A lot of it's going to be optical, and so it's nice to be able to look straight through the glass capillary. What else? It's a good electrical insulator. Right, fused silica is a good electrical insulator. And that's good because if you're applying thousands of volts here and you touch the side of the capillary, you don't want the electric field that's inside this tube to jump out and shock you, right? So it's a good electrical insulator. It's also, this is actually a pretty unique property. Usually good electrical insulators are also good heat insulators, but it's actually a poor heat insulator, or in other words, it's a good heat conductor. And that's good, obviously, for this dissipating heat property. Okay, so that's the capillary itself. There's one part of this system we haven't talked about, though, and that's because this whole thing happens in solution. So this capillary is filled with a solution. Let's talk a little bit about that solution. So it is commonly referred to as the buffer, or a little bit more of a descriptive terminology, and also somewhat older terminology, the background electrolyte. So it is or the BGE. It is the electrolyte solution that gives rise to the electrical double layer and therefore allows us to get EOF flowing through these capillaries. We've seen when we talked about EOF that pH affects the silanol. There we go, the silanol protonation on the capillary. And that protonation, sorry, haven't had my coffee yet this morning, that affects the velocity of electroosmotic flow that we're going to see in this capillary. And so a really nice stable pH gives us a really nice stable velocity of electroosmotic flow, which gives us nice reproducible separations. The other thing we should be thinking is that it also affects the acid base chemistry of the analyte. And that means that for each analyte, it affects the velocity electrophoretic. It affects the mobility basically by protonating or deprotonating generally. And so we like to keep a nice stable pH for both of these reasons, nice reproducible separations, nice stable values of electrophoretic mobility. Let's see here. So the buffer composition, the composition meaning the actual salts composition, as I said, no coffee. Oh man, it's bad. No coffee yet this morning. But the buffer composition, that is the actual physical identity of the salts that make up the buffer, the pH that we set that buffer at, and the concentration of the buffer, or as I'm going to call it, square brackets for concentration of the BGE, right, the background electrolyte. These are all major factors in CE method development. So if you have a new problem that you want to tackle with a CE separation, you are going to spend a long time, as I like to call it, I say this with my grad students who work on this kind of stuff, you're going to spend a long time in buffer hell. And that's because there are so many, like, it doesn't seem like much, right? 1, 2, 3 factors, but how many different salts can be used as a buffer, and how many different pH ranges can they take on? And of course, this is an analog value, right? So it can be, any any value. There is some chemical reasoning in how you would pick some of these things, right? So for example, if you understand your sample system and you understand its acid-base properties, that'll really help you target a pH range, right? If you want to target things like specific interactions of an analyte with a buffer salt component, that'll really help you nail down buffer composition. But the one thing I'll tell you is that honestly, the current state buffer selection is often, not always, but it's often more art than science. Is maybe oversimplifying it. I mean, like I said, there are chemical reasons why you pick one buffer over another, but this process often starts with, I like to use phosphate buffers, and so we're going to start with phosphate, and we're going to see how well it does across its whole pH range. And if that doesn't work, we'll move on to borate, or we'll move on to tris or HEPEs or some zwitterionic buffer. So the point is, it's a lot of kind of guess and see what happens. Although you will find a good amount of literature on the topic of buffer selection for CE. So let's talk about maybe one of the most important factors here, which is the concentration that we use for the background electrolyte. So, so buffer or BGE concentration is particularly important. And it's particularly important for two reasons. The first one is heating. So we know from our discussion previously that this whole thing in CE, the whole reason it works is because we found this system in narrow bore capillaries to dissipate heat. Heat is a problem for us, right? When we increase the concentration of the BGE, what that effectively does is it decreases the electrical resistance. When we decrease the electrical resistance, by Ohm's law, we increase the current, the electrical current that's going to flow through that capillary when we apply a high voltage. If we increase the current, we increase that mechanism we talked about last time of Joule heating. That is just heat produced by the electrical current that runs through the capillary, right? So if we increase the amount of salt that's in there, more current can flow through there. More current is going to lead to more heating, and eventually that's going to cause you problems. There's some threshold of heating that your capillary can dissipate pretty effectively, but that threshold is going to come at a lower voltage if you have a higher electrolyte concentration. So that's one reason. Heating is one of the two reasons why this concentration is particularly important. And what it does for us, if we consider heating, it kind of sets an upper boundary, right? We don't know what that upper boundary is. We have to do some experimentation to determine what our thresholds are before we see some, heating effects. But the point is, we can't go as high in buffer concentration as we want arbitrarily, because eventually we're going to run into heating problems. So that's on one end. Let's look at the other end, the low concentration end, because there's an effect here that can be problematic as well. So we're going to talk about a fairly advanced topic here, something that I generally don't even start out with my grad students doing CE, and that topic is stacking. So to understand what stacking is, let's consider our capillary. Here it is. We're going to inject some plug of sample. And behind this sample, there's going to be buffer. We're going to talk about these injections in a minute. After this sample, there's going to be buffer. And this zone right here is the sample. Okay, so we can think about this as 3 resistors in series. And I won't turn this into an electronics class, but I'll show you what 3 resistors in series looks like. It looks like this. Here's one resistor, we'll call this R1. Here's our second resistor, we'll call this R2. And here's our third resistor, we'll call this R3. And we can think of this as the resistance of that first buffer zone, the resistance of our sample, and the resistance of that second buffer zone. And this circuit, if you do some electronics, if you have a background in this, or if you want to just Google or Wikipedia this to kind of get an understanding of what we're talking about, this is a circuit called a voltage divider. And like I said, I won't turn this into an electronics class, but I'll tell you that in a voltage divider, voltage, the amount of volts that we apply, is, for lack of a better term, used up proportionally to the resistance value. What that means is if I apply 100 volts here and 0 volts here, we get current going in this direction. If this is my highest resistance, most of that 100 volts is gone by the time I get to here, and we're using only a small amount of that 100 volts here. So the voltage is used up proportional to the resistance of these zones. So let's consider what that means then if we are in a situation where buffer concentration is too low. So let's call this the concentration of our BGE, and let's call it too low. So here's our capillary again. Here's our sample zone. All right, that's all the mixture that we're trying to separate. And if the buffer concentration is low, it means this resistance and this resistance are very high. So that means we're going to get a high field, a high electric field in this region. And we're going to get a high electric field, right? We're going to use most of our voltage over this distance and over this distance. And in this small region where the sample is, where the mixture is that we want to separate, we're going to get a low electric field because we're going to use very little voltage. The voltage difference between, if you want to think about it as between this point and this point, is very low. Okay, and if that voltage difference is very low, then the electric field in that region must also be very low. And the problem is that we want a high field where we have this sample mixture, right? The place we're trying to do electrophoresis is amongst this mixture. It is very good to have high electrophoretic mobility in an area where there is no sample, right? We want the high field in the sample. So often, I guess we should really define this term right here, stacking. This situation is not stacking, this is destacking. Stacking actually is a good thing. So let's define stacking appropriately. So stacking it refers to selecting BGE and sample buffer to maximize local E field in the sample. That's what stacking is, and so the opposite of that, the bad situation that we've described here, is often referred to as destacking, right? So if your BGE concentration is too high, too low, if your BGE concentration is too low, you're going to end up with a disproportionate electric field that doesn't affect your sample very well, and we call that destacking. So just to put a number on this, a typical concentration of the BGE would be on the order of 10 to 100 millimolar. That's usually what we're talking about. Okay, we are going to talk in the next video about injection methods and detectors for CE.